Hello everyone, welcome to a new video. And today our topic for the day is route redistribution from the same book that we are continuing, The Network Warrior. For those who don't know, this is the book Network Warrior, which is written by Gary Donho. And this book basically outlines the topic that was missed during our CCNA preparation. These books deal with the practical information, not an in depth guide of the protocol itself. Actually, by viewing this book, I got my eye on this. Acing the CCNA examination. This is book by Jeremy McDowell, the same person who establishes or who is the reason behind my foundation of the networking information. The Jeremy IT Lab, the same book. If you want, you can get a copy of this as well. And the thing that I showed you or told you that there's a book written by the same author, O'Reilly networking. This is book about the particular protocol, TCP IP protocol stack. So this is not the topic for the day, but I just caught my eye on, so I shared with you. So without any further delay, let's go about redistribution. We have heard what a redistribution is, but in this video we will cover it in slightly more in details and depth. So redistribution is the process of injecting other routing protocol, same routing protocol with a different autonomous system or process, or third, the directly connected route, or fourth, the static route into another routing protocol to enable inter-protocol communication. So these are the scenarios in which redistribution happens. You know what a redistribution is. For example, if we primarily use OSPF in our internal network and want to share the same with external network over BGP, we have to perform the redistribution. If we set a static route and then we will need to share this route to externally, or if we use static route and share internally on OSPF, externally on BGP, then we have to do again something called redistribution. Okay, so in order to do redistribution, the Cisco iOS provides the redistribute command, and redistribute command actually asks for a metric, and metric is something by which the protocol decides which path to include in its topology table, and which after that will be recommended to RIB, routing information base. So, redistribution is configured on the protocol for which the routes are destined. No configuration is required on the source router. So, the source router is basically the router which shares the path, and the destination router is basically on which we want that route from to be. Okay, so default metric can be set using the default metric with a value command, and the value of metric depends on, for example, rip, it's up to 16 as it counts the number of hop. So because we have already studied that different protocols have their different calculation of metric, and how they calculate is totally depends on the nature of protocol, whether it's a distance vector protocol, link state protocol. So the value of metric depends on the protocol itself. We have to supply such form of metric that a protocol accepts. Okay, next is the default metric can be overridden using the custom redistribute command, which is redistribute with a protocol name, its protocol ID or the process number, then metric, and assigning a value to the metric. And again, the value varies what kind of protocol it is. RIP redistribution of the connected route will lead to unusual broadcast to the connected network with a classification and control packet, which is of IP precedence 6 or DSCP 48, which might suppress the actual IP packet. So it basically saying that if we use RIP redistribution, routing information protocol redistribution of the directly connected route or the connected route, then it will broadcast it to the connected network with classification. I guess this classification talks about the classful networking, which is basically class A network with /16 mask, class B with /24, etc. So it will lead to unnecessary broadcast, which may suppress the actual IP packet transfer, which itself is a failure. Okay, so what we can do? We can use the command passive interface for certain interfaces on which we don't want to broadcast happen. Okay, the next thing is Default metric in EIGRP requires setting up the bandwidth, the delay, the reliability metric, the bandwidth metric, and MTU, because these are the parameters EIGRP uses to calculate its metric. So we have to use, and here the value have to assign how much values for what information. For example, the bandwidth ranges from 1 to 4 billion, delay ranges from 0 to 4 billion microseconds. Reliability metric starts from 0 and goes up to 255. The bandwidth metric same goes starts from 1 and goes up to 255, while the MTU again starts from 1 to 4 billion. It's not 1 billion to 4 billion, it's simply digit 1 to 4 billion. And actually, I have short written this 4 billion. It is 4 billion something value. Okay. We have to do study a lot more today. Now, the mutual redistribution is when redistribution happen between two routing protocols in both direction. So in this scenario, the source router and the destination router, it both has to be configured, and this kind of configuration is called mutual redistribution. Actually, mutual redistribution is a very important topic when we talk in terms of tunnel networking, in which we create a GRE or IP tunnel and we advertise its or redistributes its route over the tunnel. It may link to tunnel flapping. uh, I feel like I have written that information in the same notes. So if it arrives, I will certainly tell you. Okay. So mutual redistribution may cause flip-flop back and forth between sources. If each autonomous system reports the same metric, it leads to updating the routing table each time it receives an update. So it's kind of self-explanatory. Suppose we are redistributing it, and the redistribution basically clears all its previous information and treats that the route is uh, learned by that new protocol, the destination router protocol. So what it will do, just like every protocols want to share its route, the redistributed route will be reshared to that thing, and basically the it kind of formation of a loop. And we all know what a layer loop, a layer 2 or layer 3 loops done. It flip flops the leg. So connection may come up, then it's go down, then again it's come up, and this will happen. Okay, so what we can do to resolve this issue? We can resolve this using tagging routes or filtering with route map. Let's go to each of them one by one. So route tags are the value in range of again 0, starting from the value 0 to 4 billion. 4 billion means 4 billion something 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 for use for identification. So to tag a route, we can, for example, in the case of redistributing a EIGRP route to an OSPF, we can use the command redistribute EIGRP with its autonomous system number, the autonomous system is specific to that EIGRP protocol, its metric, then the metric we want to define, then subnet, tag, and we want to assign a value of 0 to 4 billion, yada yada yada. And to apply a tag in EIGRP, we have to use route maps. Basically, and tags can be viewed using the IPOSPF databases. So basically, we have learned about how tagging use, but just assigning a tag we can use for identification, but we still have to control that route, or we can say the filter the route. In order to filter, we have to use the route maps. So I have already arranged another note in which I specifically basically ask from chat GPT or any LLM model what the difference between a route map or LA or ACL is, and I have sorted the key points that is actually the difference. Okay, so basically what I remember till now, that route maps provide more granular control over the control. So if we want to change some metrics or values inside that particular route or a particular for a destination, particular destination, we can do that via route map. while ACL simply starts or ends with the allow or block statement. So it's basically a control statement, while route map a more plastic size molds the route as per our direction. So we can set the ACL or set the MTU values, or we can do much more granular things. Routes destined to or route tag with a particular information. So basically, it's kind of processing the routing. I hope that you are understanding what I'm trying to convey. That route provides way more control than a ACL does, and that's it. And we are actually seeing one of the example of what route map is capable of. So after tagging the redistributed route, we can view it using the IP OSPF database command. So basically, we are redistributing the EIGRP to the OSPF. After redistribution, we can see that it is now showing in the IP OSPF database command. Now, to apply a tag in EIGRP, to actually application of a tag, we are using route map. The command is route-map with its name, which is a simple name that we assign to a particular route map, with its permit and the sequence number. Sequence number usually in increments of 10, followed by set tag and with a tag. And tag ranges from 0 to 4 billion. We'll tag all the entries passing through this map with the mentioned tag. And to use the above route map, we have to use the command redistribute connected route map and route map name. And what this will do, all the IPs or all the network ranges matching to that particular command route map permit sequence will automatically be tagged with the set tag number that we have just shared. And finally, few last statement for the day. Redistributed routes. Okay, so actually this is a misspelling. ROUTES. So actually I missed the U. ROUTES. Okay. So redistributed routes become external in the target protocol. Okay, so redistributed route is treated as external route, but once it gets redistributed, it becomes kind of native to that protocol. For example, when we redistribute route from EIGRP to OSPF, OSPF kind of treats it like a external for a while, but when it forwards the route or it shares the route, the next router will think that it is native from that destined router. Okay. After redistribution, the routers in the target domain treat that the route is native to that protocol, external where applicable, and forgets its original protocol for routing decision. And this is the reason why loops happens, and this is the reason why we were using route maps and is what was route tagging and route maps in order to filter that. Okay, if that redistributed copy is later redistributed back toward the origin router without any checks, and the redistributed copy becomes preferred on the origin router, of course, due to AD and metric, it can replace the native route and cause loop and instability. And finally, this can be prevented by tagging redistributed route, filtering tags, redistribution point, basically restricting redistribution in the direction or a particular scope by use of route maps or prefix list. And yes, I also want to add one point. If you want to more detail about this topic, please feel free to ask ChatGPT, Gemini, or any Claude or any assistant that you use about a scenario in which redistribution may cause layer 3 loop due to AD or metric mismatch or value. Actually, I recall a scenario in which, for example, if you are redistributing the protocol between protocol EIGRP and OSPF, because EIGRP has a administrative distance of 90, while the OSPF has an administrative distance of 110. Because of this protocol mismatch, if the route comes back and forth announcement, then there's a scenario or there's a chance loop might follow. For example, if we connect three routers in a triangle formation, one is running EIGRP while other is running OSPF, and third router actually shares the route or have a static path to both. There is a scenario which creates the loop, and feel free to Google it, feel free to study about it, because you just cannot be a network engineer just by watching some random videos or videos like mine, but by actually understanding and researching the topic. And that's a 2 cent from my end, and that is it for today. I hope you will join next day or another day. Thank you for joining. Thank you for watching.